This is the Introduction to Trigonometric Identities tutorial. A trigonometric identity is an equality that involves trigonometric functions and is true for all values of the occurring variable. Now, trig identities are one of those things in math where it's just easiest to show you the work and explain it to you that way. So the first thing you want to start with is the common trigonometric identities. These three groups here are the three most common groups that you're going to deal with. First, we have the Pythagorean identities, and these are the three Pythagorean identities. What you need to know about these identities is simply that the statement on the left is equal to the statement on the right. So, for example, in the first statement here, if you had the cosine squared theta plus sine squared theta, that will always be equal to 1. And 1 is also the cosine squared theta plus sine squared theta. Now, you can rearrange these identities if you need to. For example, you could take the cosine squared theta, and by the way, you can also substitute x for theta. So you could say a cosine squared x plus sine squared x is equal to 1. You could rearrange that by, say, subtracting sine squared x from both sides of the equation. And what you'd have is on the left, cosine squared x, because the positive sine squared x and the negative sine squared x cancel. So cosine squared x is equal to 1 minus sine squared x. Now this is completely common in trig identities. In fact, this is so common, you're going to see this kind of work in almost every problem where you're rearranging identities. You're not changing them, you're simply rearranging the terms in order to solve the trig identity. So what we did down here can be done with any of these identities, the Pythagorean identities, the reciprocal identities, and the tangent and cotangent identities. So it's best when working with these problems to have a little library like this in front of you, a little library of what these identities are. Eventually you're going to memorize them after you've done enough of these problems. However, in the beginning you really want to have them available to you as you're approaching these problems. So after Pythagorean identities, we could look at the reciprocal identities. Now these guys are pretty straightforward. For example, the secant of theta is equal to 1 over cosine theta, the cosecant of theta is equal to 1 over sine theta, and the cotangent of theta is equal to 1 over tangent theta. And again, remember, you can replace the variable theta with another variable such as x. So you could say that the cosecant of x is equal to 1 over sine of x. Now, whatever variable you choose to use, you want to use that variable throughout the problem. For example, you don't want to say the cosecant of x is equal to 1 over sine theta because that would be confusing. You'd be suggesting that x and theta have different values, and then the identity wouldn't be true. So lastly, we have tangent and cotangent identities. So the tangent identity, tangent theta, is equal to the sine theta over cosine theta. And the cotangent identity is that the cotangent of theta is equal to the cosine of theta over sine theta. So what I'd like to do next is take a look at some practice problems, and I'll show you how we use these. Let's look at this problem first. What I'd like to do is simplify this statement, the cosecant of x times the sine of x. So in order to simplify that, we just want to reduce it as much as possible. Now, I know that the cosecant of x is really equal to 1 over sine of x. So I can rewrite this as 1 over the sine of x. So this is the value of the cosecant of x times the sine of x. So you could write sine of x over 1 if you wanted, and what you'd notice here is if you're multiplying these two, the sine of x is going to cross cancel. So if you simplified this statement, you just simplify it and your answer would be 1. Notice how we use the reciprocal identity of the cosecant of theta here, or the cosecant of x, to simplify this problem. Let's take a look at another problem. Let's work with the tangent of x times cosine of x is equal to sine x. What I want you to do is prove this identity. Well, let's start with what we know. We know that the tangent of x is also equal to the sine of x over the cosine of x. So I'm going to rewrite that below in the problem here. Tangent of x is really sine of x over the cosine of x. And then we can bring down our cosine x that we're multiplying by. So we have cosine of x here, and this should be equal to the sine of x. Notice we haven't changed the problem at all. I've just substituted a different identity in here for the tangent of x. So what you'll notice is that the cosine of x is going to cross cancel here. And what you'll have remaining on the left-hand side is the sine of x. And the sine of x does equal itself. So the sine of x is equal to the sine of x. So in math, this kind of problem here with the equal sign is typically referred to as verifying an identity. So in this case, we verified this identity. The tangent identity in this case, that tangent of theta, or tangent of x, is equal to the sine of theta over the cosine of theta. Let's go ahead and take a look at another problem. Sine of x times cosine of x times tangent of x is equal to 1 minus the cosine squared of x. Now, notice already that we have a cosine squared of x. The only kind of identities dealing with a square that you know so far are the Pythagorean identities. So you want to be paying particular attention to those identities in dealing with this problem. You'll find little indicators through these problems that will help you get through them. So again, because of that equal sign here, all we're doing is verifying an identity. So in the end, we're going to get something on the left is equal to the exact same thing on the right. So let's start with the left-hand side of the equation here. We have the sine of x and the cosine of x. Now, none of our identities deal straightforward with just the sine of x or the cosine of x. You don't see the sine of x is equal to something in any of our identities. However, you do see the tangent of x being equal to something. In the tangent and cotangent identities, the tangent identity suggests that the tangent of x is equal to the sine of x over the cosine of x. So we can write our left-hand side of the problem like this. We'll keep our sine of x, and we'll keep our cosine of x, and then I'll rewrite the tangent of x as the sine of x over the cosine of x. And then on the right side, that's equal to 1 minus the cosine squared of x. So let's do some simplification on the left-hand side of the equation. Here we can cross-cancel the cosine of x and the cosine of x. So what we have left is the sine of x times sine of x, which would give you sine squared of x. Notice that the square comes after the sine. It doesn't come after the variable. So you would get sine squared theta if we were using theta right now for our variable. So on the left-hand side, we've simplified it down to the sine squared of x, which is equal on the right to 1 minus the cosine squared of x. Now notice that we've just rearranged the Pythagorean identity here. To make it a little bit easier to see, I'll just add the cosine squared of x to both sides of the equation. On the right-hand side, the negative cosine squared of x is going to cancel with that positive cosine squared of x. And on the left-hand side, we're now going to have the cosine squared of x plus sine squared of x is equal to 1. So we verified that Pythagorean identity, that the cosine squared x plus sine squared x is equal to 1. That was this guy right here. So now that we verified that, the problem's done, because that's the intention of this problem, is to verify that identity. Let's take a look at another problem. Alright, so what I'm trying to do here is step up the level of difficulty in these problems a little bit. And you're still using the same identities, so you haven't made it any more difficult in that way. It's just a little bit more difficult to see these. You've got to apply a little bit more mathematical reasoning. Now again, remember to look for indicators in your problem of what kind of identity you may be using. So when you see this squared here, you automatically know that we're going to be dealing with Pythagorean identities. So again, let's start on the left-hand side. I'm going to start with that term, the cosine squared of x. Now take a look at our Pythagorean identity here. If I wanted to get the cosine squared of theta by itself, I'd simply subtract sine squared theta from both sides of the equation. And when you did that, what you'd get is the cosine squared theta is equal to 1 minus sine squared theta. So I'm going to replace cosine squared theta here, our cosine squared of x, with this value right here, 1 minus sine squared x. So this becomes 1 minus sine squared x. And then I'm going to bring down our minus sine squared x continue that guy, so minus sine squared x is equal to 1 minus 2 times sine squared x. Alright, so we'll combine our like terms on the left-hand side. I have a negative 1 sine squared x and another negative 1 sine squared x. So what I really have is negative 2 sine squared x's. So we have 1 minus 2 times sine squared x on the left-hand side is equal to 1 minus 2 times sine squared x on the right-hand side. Whenever you have something on the left equal to itself on the right there, the same thing, you've proven your identity. I'm going to go one step further to make this a little bit easier to see. I'm going to add 2 sine squared theta, or sine squared x in our case, to both sides of the equation. On the left-hand side, the negative 2 sine squared x is going to cancel with the positive 2 sine squared x, and the same thing is going to happen on the right. So what we'll have is 1 is equal to 1. And that's obviously true. Now you may be looking at these problems and saying, oh my god, I don't see how he sees this when he's doing this. I don't see how to set this up. Well, that's because I did it on paper and worked it out before this all got done. The reality is that even when you've been doing these for years like I have, you have to sit down and work through these a couple different ways. You have to consider a couple different angles, play with the different identities that you know of until you find one that fits, that really simplifies and cuts these identities down. Very few people, if anyone, is able to automatically look at these when they get started and know exactly the direction that they're going to go, especially as we get into more and more complex identities here. And that's my goal, is to slowly build you up to dealing with more complex identities. So don't feel bad if, it looks like I'm just looking at these and know what I'm doing. It's because I practiced them before I started this tutorial. And that's the reality of this. That's the reality that you're going to deal with as well, is that you're going to have to work these out on paper. And it may take you a little while, but don't get discouraged when you do it. It can be kind of fun if you consider it to be a puzzle. Now let's take a look at one last identity. Here we have the cosecant squared of x minus 1 over cosecant squared of x is equal to cosine squared of x. And what I'd like you to do is verify this identity. Alright, so let's start with the numerator of our fraction here on the left, cosecant squared of x. Now, the cosecant of x, or the cosecant of theta here, is equal to 1 over sine of theta. So, cosecant squared of x is really just 1 over sine squared of x. So I took this same identity here, this same fraction, 1 over sine squared, or sine theta, and I applied that square to right here. Alright, so that deals with the cosecant squared of x, but we still have that whole thing minus 1, all over the cosecant squared of x. So again, I'm going to take that cosecant squared of x, and I'm going to write it as 1 over sine squared x. Alright, so I want to combine these two values in my numerator, 1 over sine squared x and that negative 1, but I need to have a common denominator for both of them. Right now, this just has a denominator of 1. So what I'm going to do is multiply this fraction here, that 1 over 1, by sine squared x over sine squared x. I can multiply it by sine squared x over sine squared x because sine squared x over sine squared x is equal to 1. And when you multiply something by 1, you're not actually changing it. So we multiply directly across here. So on top, the numerator here of our new fraction, I'm going to have 1 times sine squared x. So I'll write this body over here on the left first. I'll do my work down here. We have 1 over sine squared x. That came from right here, our 1 over sine squared x. Minus 1 times sine squared x, which is just sine squared x, over 1 times sine squared x, which again is just sine squared x. And that's all still over our 1 over sine squared x. Alright, so now we want to combine our fractions on the numerator, and because they have like denominators, we can combine those fractions. So, up top, we have 1 minus sine squared x. So 1 minus sine squared x. And on the bottom, we have a common denominator of sine squared x, so we just keep that common denominator, sine squared x. That's all still over 1 over sine squared x. Now, if you recall, you cannot have a fraction in your denominator. So we're going to invert that denominator and multiply. And before we do that, remember that all this stuff on the left-hand side is still equal to the cosine squared of x. Alright, so we're going to invert this bottom fraction here, and we're going to multiply to get rid of it. So, we're just going to multiply this top fraction now by a sine squared x over 1. And all this is going to disappear now. So our sine squared x is going to cross cancel. And we just have 1 minus sine squared x for the left-hand side. So all of this work here, this whole thing right here, all the work that we did, reduced to a 1 minus sine squared x. And that's equal to our value cosine squared of x there, cosine squared of x. So, take a look at this guy right here. This is the Pythagorean identity, and we're going to be using that. That's exactly what this guy is. So I can show you that. What I'll do is I'll just add sine squared of x to both sides of the equation so I can get rid of it on the left-hand side there. So I'll bring it down here where we have more room. Our negative sine squared of x canceled on the left-hand side, and we have just 1 now. And that's equal to the right-hand side, where we have a cosine squared of x plus sine squared of x. Alright, so sorry about running out of room there. Some of these problems take a lot of work. And now remember, I didn't just make that work up off the top of my head. I worked this one out on paper before I got started. That's the reality of the situation that you're dealing with here. Take a look at your problem. Formulate an idea of how you want to get started by switching in some of these different identities that you've just learned, these common trigonometric identities, and then work the problem out and see if you can get it to, in the end, verify the identity. So in the end, you're either going to get something equal to itself, like 1 equals 1, as we've seen before, or you're going to get an exact identity in here, like we just got. 1 is equal to cosine squared x plus sine squared x. That's going to happen a lot, and that's what you're going for when you're verifying identities. Simplifying, like we did in that first one, is kind of the easiest step. That's what you work up with to get yourself into verifying identities. Now in the last part of this tutorial, I just want to show you one more type of identity, and those are called the cofunction identities. Here are your cofunction identities, and they're all pretty straightforward. You have some sort of a trigonometric value, like sine, and you multiply it by pi over 2 minus x, and it could be pi over 2 minus theta, just whatever you prefer to use for your variable. And that'll be equal to its opposite trig function. So these are the 6 different cofunction identities. I'm not going to do any problems with them because you know now how to use trigonometric functions and trigonometric identities to verify trig identities. So if you see this expression in a problem, you automatically know that you're going to be using cofunction identities, and you know how to substitute these values in for those problems. Now I'm going to show you another type of identity. These are called the even-odd identities. So there are 6 even-odd identities, and the easiest way again to show you these even-odd identities is to work through a practice problem with you. So in this problem, I'd like us to verify this identity. Cosine squared of negative theta plus sine squared of negative theta is equal to 1. So I'll begin by rewriting our problem over here. Cosine squared of negative theta plus sine squared of negative theta is equal to 1. Now, let's just see if all that works out over here on the right. I'm going to set this equal again, and I'm going to bracket some information off. Let's take a look at that square when we just place it right here. And remember, you can do that. It's common to write it as cosine squared of negative theta here, but it's just the same as writing it as cosine of negative theta squared. So we'll write it as the cosine of negative theta. And we've got all that squared plus the sine of negative theta, and again, we're just going to move that square outside the bracket here. So when you do that, you know that the cosine of negative theta is equal to the cosine of theta. So this whole piece of information, that cosine of negative theta, really just becomes the cosine of theta, and the square still applies. Plus, now the sine of negative theta becomes negative sine theta. So we have negative sine theta over here, and that's squared. So if you follow that out a little bit, you'll get the cosine of theta squared plus sine of theta squared. Now it's positive sign instead of that negative because anytime you square a value, whether it's positive or negative, you always get a positive answer. For example, negative 2 squared is negative 2, so negative 2 squared is negative 2 times negative 2, which gives you a positive 4. Same thing with negative sine theta times negative sine theta. You get a positive sine theta squared. And you know from our Pythagorean identities earlier on in this tutorial that cosine theta squared plus sine theta squared is equal to 1. So this does check out. We verified this identity. It's a combination of even odd identities and a Pythagorean identity.